This lecture is on data recording and signal transmission. As you know, in machinery condition monitoring, it is very important that we get the data out of this machine and then record it, so that we can do the signal analysis on it. Well, so what is the format of recording is what we are going to discuss in this class. What are the methods to record such a signal, and then how do you do the analysis. You all recall that in computer aided data acquisition, we notice the importance of sampling frequency and then the number of data points. This plays an important role in the selection of the data recording media or format. Well, before we come to this idea, I would like to tell you something about the traditional techniques of data recording. Well, you all must have visited certain plants. Could be a power plant, could be a steel plant. So, they have a control room in which I am talking about things in the industry about 3-4 decades ago, and then all they had were a lot of analog meters, essentially RMS or peak meters, and data logging was done by plant personnel. This was the format of data recording maybe a couple of decades ago. Okay. But now, what they were doing there is, as a function of time, they would note down the parameters like the current drawn by a motor, maybe the temperature of the bearing, maybe the supply voltage. Okay. And this time, mind you, was maybe every 30 minutes. So, every in hours, and this was being done by a human being. And if there was this should be the log sheets. They would essentially form the log sheets, and then and these were available in the plant room. And then if there was an abnormality at certain conditions, people would go back to a certain date and look into the log sheet of the plant, and then try to come to a conclusion like what went wrong and so on. Or suddenly if in the plant operator notices that the temperature is suddenly rising, okay, it's increasing, then they would set an alarm condition, and then people would take precautionary measurements as to how to reduce this kind of abnormal behavior of the machine, or how do you control them. But there were a lot of problems with this. This was a completely manual mode. Okay. There are problems in which human errors could creep in because of wrong recording, wrong writing, wrong reading. This was one possible. Another was it was tiring. and cumbersome, because visually you have to read all the meters in the control room, and in the control rooms could be panels of meters and so on, and this was a very cumbersome and tedious process, and then there are a lot of chances by which errors could creep in. And there have been instances where people have reported that because of a wrong reading recorded by a person, the interpretation was wrong, and then the analysis of the prognosis was not correct. Well, another method was there were, other than writing. So, the first one was human intervention with physical data logging. But closely with this is using either a printer or a strip chart recorder. These were the analog, okay, and wherein there will be just a voltage signal coming out because of the parameter, and then with time basically there will be a paper roll, okay, which will be moving at a certain speed v meters per second, and then there will be pens on this, and they will be writing or plotting the parameters, and this would be on the roll. Okay. Okay, and this is essentially what is a strip chart recorder. And then people used to have such large rolls of data, wherein we can look into the problem and then find out, get basically a time history of the signal by looking at the strip chart recorders. And some of these data logging meters used to have trip set, tripping levels or alarm levels set, preset. That means, when the alarm level increased or the signal level increased, beyond the set level, it would trigger an alarm. And this was what was the traditional method of I would say data recording. But as you can see, the problem with this kind of data recording is, if I was to list down, one was lot of scope of human error, it is manual, thus tedious, time consuming, it is not real time, it is difficult to obtain past data, because then one has to physically pull out the log sheets, and that would be cumbersome. And then because of large amount of writings, archiving, or storage issues present. Okay. Now, because of this disadvantages, since the 60s, people have started to use other means of recording, and that was the machine mode, and first would be a tape recorder. Okay, like the spool or the cassette. Of course, cassette came much later, and the spool type tape recorder. Okay. Now, we will look into these different types of tape recorders, and then what is the present format of tape recorder, and how we do the digital recording in such tape recorders. So, if I was to look into the different formats of data recording available today, one could be the analog recording or the digital recording. What happens in the analog recording? We used to have the direct recording method, wherein on a cassette or a tape recorder or a spool type tape recorder, the data was stored because of the hysteresis in the ferritic tape. Because the signal would be converted, basically essentially we have a voltage signal, which is time varying or an AC voltage. This could be my voltage signal, which has to be recorded. Now, because of this varying voltage, there will be an magnetic flux created when the signal is recorded through the head of the tape recorder. So, we have a magnetic head, and then the tape is made to go at a particular speed, okay, and the take up spool and the home spool. Okay. And they go at a particular speed, and some of them could be 6.77 inch per second, and this is a value of the industry format. Then it was in the inch per second speed, linear speed, and this is dependent on the RPM. We used to have the old LPs at 45 RPM or 33 and 1/3 RPM, etc. So, these are the particular speeds at which these things used to run. Of course, in the I am not talking about the LP spools, because in LP spools what happens, the data once stored cannot be erased or changed. Okay. But we are not talking about the LP spools in this case. We are talking about in head, wherein because of the magnetism introduced in the ferritic tape, the data could be stored. And then of course, we also have the possibility of having an erase head. If the erase head is there, you could demagnetize it, and then the tape, the information stored in the tape could be removed. But the advantages or disadvantages of this kind of systems are, this had a very poor dynamic range. By dynamic range, I define as the highest recorded signal level to the lowest recorded signal level. Okay. And they were also having a frequency limit. like an upper limit and a lower limit. And traditionally these magnetic tapes had a very low upper limit, could be as low as 10 hertz and maybe as high as maybe 12 kilohertz, so on. And this later on improved with the type of tapes. There were metal tapes, chromium tapes, etc., wherein this could be go up to maybe 17 kilohertz. But traditionally this direct recording tape recorders were used mostly for recording audio signals. And as you know, the audio signals are in the range of 20 hertz to 20 kilohertz. And these recorders did a good job in recording such audio signals, or for that matter any signals which were in this frequency range. So, when you are talking about machinery condition monitoring, we could be recording signals from noise or acoustics, sound signals, vibration signals, and maybe temperature signals or certain process parameters like pressure, etc. And our requirement is that with each device we have to either reproduce the original signal. But the problem is this direct recording was data storage, because once we store it in a magnetic media, there is every possible chance that in a magnetic environment they may deteriorate. The physical tape may get corrupted because of moisture, high temperature, etc. You must have seen, if you are at home, if you store your old, and if you ever have your old spool tapes or cassette tapes stored elsewhere, you will see if you do not care about the moisture around, there will be a lot of fungi formation on those tapes, and then there will be you will lose the signal quality, etc. And these are the problems. And of course, from a signal processing point of view, the major problem is it cannot record the low frequency signal. But in the early 70s or the late 60s, these spool type direct recording tape recorders were quite popular, because that was the only technology available then, and they were doing fairly a good job with recording audio signals, particularly music recordings, etc. Of course, if you want to then have a permanent recording in the media, people use this the record player, the records, the LP records, the EP records, etc., wherein permanently the song tracks could be cast and kept in those vinyl discs. Okay. But we are not talking about, we obviously cannot store data, because data has to be recovered for our analysis, and we do not want to record it permanently in a recording media. So, that the provision of erasing was not possible in the LP records or the EP records, but in the direct recording, by having this erase head, we could have always erased the data recorded. Then coming back to the next format of recording, that is the FM recording. That is the frequency modulated recording. The FM recordings are very popular and convenient because they can measure as low as DC and then can go as high as maybe 12 kilohertz, etc. So, low frequency recording are possible by the FM recording. Of course, the recording media could again be a spool or a cassette tape and so on, but the advantage is the low frequency recording could be done and it has a relatively high dynamic range. So, this was popular from the maybe from the 70s to the maybe mid 80s. People used to use this FM recording for recording the signals. This is from mid 70s to 80s. People were doing the FM recording. But then this later on from mid 80s, we have come up with this format of pulse code modulation recording. Which were essentially an high frequency recording used in the in the video recording. People use the same pulse code modulation technique which was used in video recording for recording audio signals, and people then use them in DAT recorders or digital audio tape recorders, and these are quite popular till very recently, maybe till about late, or maybe I would say till the year 2000, they were very popular digital DAT recorders. Okay. And the advantage of this DAT recorders are they are DC to about 20 kilohertz range, high dynamic range, compact, and so on. Okay. If you see here, I have just made a comparison in this slide on the data recording methods by the direct recording, the frequency modulated recording, the digital recording. The lower frequency limit in direct recording is about 20 hertz, upper limit is 20 kilohertz. Noise floor is 10 millivolts, that means you cannot record any signal less than 10 millivolts. Dynamic range is very poor, 40 decibels, and time compensation is not available. Whereas in frequency modulation recording, I can go as low as DC or 0.1 hertz to about 12 kilohertz. Of course, this has improved lately. Again, noise floor is 10 millivolt, but then we can have a very high dynamic range of 80 decibels, and time compensation is possible. The digital audio recording or the DAT format which we use can have a low frequency limit of DC, and then the high frequency limit is 20 kilohertz. Noise floor is 0.1 millivolt and 100 decibels. But the advantages of the digital recording over the other recording is that the noise floor being very low, we can have signals from devices like thermocouples, as you know, thermocouples give a very low millivolt signal, okay, as opposed to maybe an accelerometer. maybe 10 millivolt. Okay. And if I was to, for a good comparison, these are basically low frequency signals. And these are relatively high frequency signals. Okay. Now, having a signal less than or around 0.1 millivolt, it would be very difficult to measure either by FM or direct recording. But you have a digital audio tape, you could record such low signals in low frequency as well as high values and at high frequencies, because they have a high dynamic range and then low noise floor. But all these three types of tape recorders are available in the market. I mean, of course, it will be very difficult for you to find a digital a direct recorder or an FM tape recorder with a spool or the cassette nowadays. But even finding a DAT recorder could be difficult at times, because nowadays people are using the DVD recorders or totally recording in a flash card or a compact media, or even writing it straight to the hard disk of the device. Okay. But the advantages of these recorders are they are portable, low power consumption. Some of these recorders can be even powered from the 12 volt DC adapter given in your car. So, the mobility of such recorders is excellent. Okay. Because why do we have this data recorders in the first place? We have this data recorders because we cannot possibly go to the plant, maybe the plant is a coal mine, a very dusty environment. We cannot go and sit next to a crusher or a grinding mill and do the vibration analysis as to find out the remaining useful life of this crusher or the grinding mill. Rather, have the transducers mounted around the grinding mill or the crusher, and then record the signal on a tape recorder, and then this tape recorder obviously has to be portable, has to be lightweight, could be powered by any source, and then once we have recorded it in a particular media, we can bring this tape recorder back to our laboratory, wherein we can do the signal analysis and try to find out the condition of this machine. So, it is not that the tape recorder is fixed or tape recorder is always there in the lab. No, this is not the objective of our recording here. Our recording in condition based maintenance or monitoring is to have a big steel plant, for that matter, next to you sitting in your analysis office. Okay. Obviously, I cannot bring a steel plant to my office, but if I have recorded the signals in a tape recorder which reproduces the signals as they were recorded or as they were measured right at the steel plant, my job is done. And with that objective, actually we are recording this signals, and then we will see what are the advantages of using a portable recorder with high dynamic range, where the data can be stored for long of time. So, right in the beginning of this class, I had told you about the importance of two factors. One is the sampling frequency and other is the number of data points. Okay. If you will recall, because I need to do signal analysis, that means if I have a signal like this, some signal, this has to be sampled at a fixed interval this has to be fixed at the sampling interval, and the total time of this data, total time is t is equal to n times delta t. This t is equal to n times delta t, where n is the number of data points. In the previous diagram, all those crosses I had done, they were actually the locations of the sampled digital data. Okay. So, in terms of the storage memory requirement, because this digital data has to be stored in some memory location in the digital recording. Now, if every data requires 16 bits or 2 bytes of memory space, okay. Suppose I am sampling at Fs is equal to maybe 100 kilohertz. Okay. That means delta t is equal to 1 by 100 kilohertz. So, 1000 10 to the power minus 5 seconds is my sampling interval. And if I was to find out the total time is equal to n times delta t, n is equal to the total time by delta t. Okay. Now, if I want to record 10 minutes of data at a sampling frequency of 100 kilohertz, my number of data which has to be stored is 10 minutes, 10 into 60 seconds into 1 by delta t, which is 1 by 10 to the power minus 5, that is 600 into 10 to the power 5 data points. Now, if every data point requires 2 bytes, I will require the memory required to store 10 minutes of data sampled at 100 kilohertz in a 16-bit recorder would be 2 into 600 into 10 to the power 5 bytes. Okay, I would though know 1 kilobyte is equal to 1024 bytes. If I approximate it as maybe for the sake of discussions, maybe 10 to the power 3 bytes. So, the memory required would be 2 into 600 into 10 to the power 5, that is equal to about 120 into 10 to the power 6, approximately 120 megabytes. MB, though I have used an approximate that 1 kilobyte is 1000 byte. That is not quite right, but just for the sake of this discussion is actually 1024 bytes. Okay. So, approximately to summarize, to store 10 minutes of data sampled at 100 kilohertz in a 16-bit digital recorder would require approximately 120 megabyte of digital memory. Okay. Now, you can now multiply. Now, if you want to, instead of 10 minutes, you want to make it 100 minutes, there will be another extra 0 coming here. If you want to sample at a still higher frequencies, your because n is equal to t by delta t or t times f s. Okay. If your sampling frequency is increased, n would increase. If your time is increased, n would increase. So, depending on that, you can do a calculation and then try to understand what is the amount of memory required. But in digital recording, the most limiting factor is the sampling frequency. In digital recorders, depending on our frequency of interest or depending on the frequency of interest, we can have this sampling frequency decided from the Shannon sampling theorem. Now, suppose we are talking about the mechanical signals basically in the audio range from 0 to 20 kilohertz. Maybe we sample at sampling frequency f s is equal to 44.11 kilohertz, and this is a set sampling frequency, and then we can record as much as we want, provided we have the memory space. But nowadays, there are very high sampling devices which can sample at about 100 mega samples per second. Okay. And this is the present state of the art. Is we can have A to D systems, A to D card, which can sample at about 100 mega samples per second. And then these high samplings are actually used for studying ultrasonics, because ultrasonics occur at frequency below or greater than 20 kilohertz, or if you want to study about acoustic emission, which occur from anywhere from 2 to 5 megahertz. So, if I was to record any ultrasonic signals or capture an acoustic emission phenomena, I have to be sampling at very high frequencies, could be 100 megahertz and so on. And these A to D cards are very costly, very difficult to find at times. Nevertheless, nowadays systems are coming in where such sampling devices are there, and then we have to store this data in data recorder, data points and data points. And from the previous example, you just saw that by playing around with the number of data points, by playing around with the sampling frequency and the time which you require to record, we can increase the number of data points. Now, so how do such digital data recorder replace the conventional, you recall the analog data recording people are doing by hand. How does it replace? How does it replace analog recording? So, in this data logger, which we will call, I can decide frequency of storage, maybe continuously, and imagine I have a signal which is low frequency content, and another which has high frequency content. Like the case of the thermocouple and the accelerometer. So, depending on my interest, low frequency content could be sampled at a low frequency, high frequency content could be sampled at a higher frequency. In the same data logger, the number of input channels is also a very important characteristics. For example, there are 16 channel recorders, even there are 128 channel recorders and so on. Okay. That depends on the interest. Of course, all the previous examples we have done with one channel. If simultaneously I want to record 16 channels of data or 128 channels of data, I need to also record them and multiply the number of data points by the small n, where small n is the number of channels. And this data points has to be stored in a memory which is RAM memory maybe. So, which could be erased, and then if you want to have a permanent record, you can write to a CD, DVD, okay, or even put it in your hard disk, or maybe also in a memory card or a device. Nowadays, you get cameras, flash cards with 32 GB or 64 GB storage capacity. Okay. And these are traditionally, compared to the data recording facilities we had in the 60s, wherein a typical spool or a cassette tape would at most have 60 minutes or 90 or 120 minutes of data could be stored. Okay, this was the duration of the spool cassette type 60, 90, 120. Obviously, we cannot do continuous data recording over months in such recording because of the limitation of the storage space. But nowadays, with such compact memory cards with capacity of 32 or 64 GB, 64 GB would last you quite a maybe I'll just show you an example in the data recorder how this can be stored. If I come back here, this is a typical data channel recorder which we have in our laboratory. This is where the digital cassette tape goes in, and if you will see here, there are 8 channels of input and 8 output channels, and then you can record about 120 minutes of data in each tape at a maximum frequency of 20 kilohertz in each of the 8 channels. Okay. So, the number of channels times the frequency bandwidth is a constant in these kind of DAT recorders. So, it is 8 channels at 20 kilohertz. Okay. And then you could be, if you want to make more channels, if you want to make 16 channels, it has to be sampled at 10 kilohertz and so on. Okay. So, this option can be there, or 32 channels at 5 kilohertz. Okay. But the limitations of such DAT recorders are, I obviously cannot record for months together. Recorder is not possible, and then I obviously cannot record at very high frequencies, maybe in megahertz. Okay. And then of course, again this has to be stored in DAT tapes, which could be contaminated. So, of recently, quite in the last maybe 5-6 years, people are using this digital DAT recorders, like you see one which we have in our laboratory here. You can have 16 channels of record, and then you can give in signals, and for such a recorder, we can have very high sampling frequencies, and then we can record a lot of data points. Just give an example. For this digital data recording with about 2 gigapoint of memory space, there is a provision of changing the sampling rate, okay, 100 mega samples per second or 10 mega samples per second. With single channel, I can be recording at 20 seconds of data, 100 mega samples, megahertz per second. It's a very high sampling rate, whereas even we are happy with 5 kilo samples per second. Even if you, for a mechanical signal, if you sample at 100 kilo samples per second, with single channel you can record 5 hours of data. Okay. And if you are running a very slow phenomena like monitoring temperatures, 200 samples per second, that itself is very high while monitoring temperature. You could be recording with single device for about days without worrying about your memory space, about the reproducibility of such signals, and so on. A very important point comes in this recorders is the how do you determine the frequency response of the DAT recorder. You could also try this with the digital recorder. A simple way to do this is, suppose we have a DAT recorder. All you have to do is record a random noise signal at the input, and then play back the signal output signal, okay, and then simultaneously plot this as a function of frequency playback signal by the input signal, and you will see a frequency, because the playback has to be of the same level as the random noise signal, and if you have recorded a random noise of a particular bandwidth, you will see and in a dB scale this would be 0 dB, this value, because log of 1 is equal to 0. So, if playback is of the same level as the input signal, it will be 1. So, it will be 0 decibels. So, this is the useful frequency limit of the signal. This check, a researcher actually does this, but it's a good idea to check it out. If you have an FFT analyzer, you can also see if you have an FFT analyzer, you can also see the phase response. So, the phase of the transfer function between the playback and the input. And this phase angle should also not vary, and this usually this phase angles typically are of the order of 2 to 3 degrees. So, then you can see the frequency limit of the signal. So, the upper frequency limit is decided by doing such a small test using a random noise in a DAT recorder, and you could use that same technique in a digital recorder as well. And there should not be any crosstalk between the channels. Now, once we have recorded this signal, we also need to transfer the signals, and usually the transmission rate of the signal or signal transmission rate depends on the number of channels multiplied by the acquisition rate and the resolution. So, the data transfer rate, even if it is given in bits per second and acquisition rate in samples per second, resolution in bits per second. So, the data rate transfer rate, transfer or transmission rate is the number of channels multiplied by the acquisition rate multiplied by the resolution. And acquisition rate, it is the unit is samples per second, and resolution is bits per sample, and the units of data transmission rate is bits per sample, bits per second. And usually when we use wireless for data transmission rate, we have about the maximum level of 10 Mbps or 1 GB. So, we can decide what would be the sampling rate, and this is the limitation of the present day data transmission by signal by wireless transmission as to the maximum data transfer rate available to us, and which is about 10 Mbps or 1 Gbps, and then this depends on the number of channels of data you are transferring, the acquisition rate, and resolution. Typically, the resolutions nowadays people use is about 16 samples per second or 24 samples per second, and the sampling rate for a low frequency signal, it is easier to transfer by wireless. But when we are talking about high frequency signals, you want to sample or send in 10 channels of vibration data over the wireless, the data transmission rate of the present wireless technology is limiting these levels of data transfer. Okay. And so that would conclude our discussions on the signal recording in the analog digital domain and the signal transfer by the wireless. Next. Okay. Thank you.